Word on this computer. Okay. Thing is, I don't see the record start video.
I see the recording icon.
You do see it on? Okay. All right. Okay. Boy, you can see it, but I can't see it. I hope that's okay. Well, I hope somebody records it in case I'm not recording it. All right, so let's see. Let me go back to the last thing that we maybe didn't do last time was the case of, suppose we start with an infinitely differentiable initial wave function and see how it evolves with time. Well, an example of such a function is 3.109, and its Fourier series is very simple. It just has three terms. You just expand the cosine, and this is the n equals 0 term. And but on the other hand, each of these terms will evolve in time differently, because when we project it onto the eigenfunctions of the Hamiltonian, which are the sine functions, we get these funny coefficients. And so the final form, of the wave function at time 0 is this. And now each coefficient evolves according to e to the minus I et over h bar. And in fact, I think I'm missing a 1 over h bar here. So let me write that down. In any event, it's absolutely convergent for all times. And let's see, did I graph that? It's in figure 3.9. 3.9 is the Fourier series for time 0 with just a 10-term approximation. And then here we have the evolution in time of this smooth Fourier series. And you can see it, as you'd expect, it because we didn't put in any artificially high momenta due to discontinuities in the initial wave function, we have smooth evolution in time. Okay, so let me go back to the Dirac delta function business. Let's see, I'm not seeing any of your comments, so I guess I'm just going to have to ask you guys to shout anonymously if you have questions about anything or suggestions. So Dirac's delta function, it's really, as I said, not a function, but a functional. A functional associates a number with each function in a space of a certain size or extent. And in particular, delta of x minus y is the functional that associates the number f of y with the function f of x. And we normally in physics write this association in this way. And they pop up all over physics. If you write the identity operator as an outer product of eigenstates of position, and you multiply from the right and the left by a Brock y and a ket f, you get this expression here, which tells us that yx yx is a delta function. That is to say, it turns the function f of x into the number f of y. And if we now combine, now use the Fourier series formulas 3, 2, and 3 to write f of x as its Fourier series, and then write each f's of n as the inverse Fourier transform of the function, which f of x, which then is this infinite series. What we get is this expression, namely the function f of x is this big sum times times f of y when you integrate from 0 to pi over 2. These phases are periodic, and so it would also be true that f of x plus 2 pi L is the is given by the right-hand side. And this thing then on the right-hand side is the periodic extension of f, not, and it's not f of, it's the same as f of x if f of x is periodic, but f of x is not periodic, then it is, if f of x is not periodic, then it's just the periodic extension of f of x. And so by comparing these, by looking at this formula, what we see is that this infinite sum of phase factors is an infinite sum of delta functions. And this is called the Dirac Comb. And if you write it more simply by setting y equal to 0, you then get this expression. Or you put it in an L, you get that expression. And as I graphed that here, and notice that these, the scale here is, this is 35,000 and minus 1,000 here. And, but the oscillations, which we can't, this is a Gibbs, these things on the bottom are Gibbs overshoots, but they are of such high frequency that they don't contribute when you integrate f of y over this, these Dirac combs, they don't, those high frequency terms don't contribute. And they go away in principle in the limit of infinitely many terms in the sum. We can then, to form this sum and get Parcelable's identity. So the sum of the complex conjugates of the Fourier function, Fourier coefficients of the function f times the Fourier coefficients of the function g then are given by these standard formulas for the stretched Fourier transform. And then if we combine them together, we see we've got this Dirac comb, but only the L equals 0 tooth of the comb contributes here. And so what we get is the sum of fn star gn is the integral of f star of x g of x. So let's see, I'm a little nervous that I haven't heard any feedback of any kind. So I haven't heard any chat or anything from the students. Is everything okay? You guys, can you hear me? I see there are 13 participants. Can you guys hear me?
Yep.
Yes, we can hear you.
Okay, wonderful. All right, all right. Well, I don't know, wonderful maybe is an exaggeration, but I'm glad you can hear me. All right, well, I'll go on with this then. So what we get here then is Parcelable's identity, which is the sum of the, so to speak, dot product of the Fourier coefficients is the dot product of the functions where you sum over all x's or integrate over all x's. Here you sum over all n's. And so Parcelable's identity then is that the integral from 0 to L of the absolute value squared of the function is equal to the sum of all the absolute value squared of all the Fourier coefficients. And now you see why it is that the Fourier series, and for that matter, the Fourier transform, naturally apply to square integrable functions, because you'd want both, for both sides of this, for this equation to make sense, both sides have to be finite. Derivatives of delta functions. Well, derivatives of delta functions are defined in such a way that as long as the function f of x is sufficiently smooth, then these equations occur just automatically. It's like, it makes integration by the definition of the delta function, the derivatives of delta functions makes integration by parts automatic. So the nth derivative of the delta function of x minus y, you integrate by parts n terms, you get minus 1 to the n, the nth derivative of f of x, and bingo, that's minus 1 to the n, the nth derivative of f of x evaluated at y. no surface term. And something that isn't so well known is that Dirac's delta function sometimes appears quite unexpectedly. For example, the general solution to the equation x f of x equals a of x is a of x over x plus b of x times delta of x, in which b of x effectively is a constant because it only is non-zero when x is equal to 0. And similarly, the general solution of x squared f of x equals a of x is a of x over x squared plus b of x over x delta of x plus c of x delta prime of x, in which delta prime is the derivative of the delta function, b of x is continuous, c of x has a continuous first derivative, and xb of x equal to xc of x equal to x squared c prime of x all vanish at x equals 0. Well, that's a big mouthful. Anyway, let me skip to something. I've been rewriting the examples section here. So let me pop over here to the examples for a little more about the delta function. Well, this is what I was saying today, just sort of reinforced, but since it's so important, I may go over it redundantly here. If we expand f of x as a Fourier series, the Fourier coefficients are given by that. We then take these guys, stick them in here and form a double sum and, or a sum and an integral. We then get this equation and conclude that this is the formula for the delta function, or more generally, we have a Dirac comb. And so that's the Dirac comb formula. Let me now generalize this because when Fourier invented this, that was the first example of such things. But now what we know is that there are, of course, infinitely many sets of orthonormal functions for infinitely many vector spaces of functions. And if these functions are orthonormal, then they span a vector space of functions that can be expanded as coefficients times the functions. So this is a generalized Fourier series. And now if we do that, if we ask, well, what are those coefficients? Well, f of x times h star n of x, we integrate, these are orthonormal, and that's fn. So the nth Fourier coefficient is the integral of f times the complex conjugate of hn of x. And now if we form that double sum, we get f of x is fn hn of x, but that's an integral dy, f of y hn star of y hn of x. So we have this sum here. And now comparing the two, that gives us a delta function. The only difference is that the orthonormal functions in general are not periodic. And so we don't have quite the same, we don't have a Dirac comb again, although we might, depending on what the special properties of the HNs are. But in general, we just get this relation. Here's another example of a Fourier series for a smooth function. Okay, let me drop back and give you an example from chapter 2. This is an example that I cooked up just recently. And if there's ever a third edition of my book, this will go in the third edition in chapter 2. And so what I want to do is I want to use the delta function formula, namely that the delta function of r minus x is minus Laplacian of 1 over the absolute value of r minus x, to write an arbitrary vector field as an integral over all space of this expression. And now what we can do is we can say, well, these are these derivatives here, since they're double derivatives, they can be either with respect to x or with respect to r. If we assume they're respect to x and we pull them out, then they're just differentiating with respect to x. And now we can use our formula for the Laplacian of a vector function, which was formula 2.49. And we can then write v of x as minus the gradient of the divergence of v, which is this expression, minus the curl of the curl of v, which is the curl of this expression. And so what we've done, therefore, is we've shown that it's possible to write any three-dimensional vector function of three-dimensional space as the gradient of a scalar plus the curl of a three-dimensional vector. And the scalar field is minus the divergence of this integral, and the vector field is the curl of this integral. And this is called the Helmholtz decomposition. Helmholtz was a remarkably productive scientist. He did work in electricity, mathematics, and medicine, and probably several other fields. So he was quite proficient. So I think that's all that I'm going to do about this. The next topic then would be harmonic oscillators. And I hope you've all seen harmonic oscillators in some form. Let me give you them in this present form that's, I think, relevant for many things that you may encounter in your studies of physics. First of all, we have the Hamiltonian for the harmonic oscillator is p squared over 2m plus a half m omega squared q squared. Q is a position operator, P is a momentum operator. The commutator of Q with P, which is, of course, defined as QP minus PQ, is IH bar. And that implies that the lowering and raising operators, defined in this way, obey the commutation relations A dagger is 1. These are also called annihilation and creation operators because we use the same notation in quantum field theory. And so the Hamiltonian for a harmonic oscillator is h bar omega times a dagger a plus a half. A dagger a has integral eigenvalues and just counts the number, counts the level of the state. The eigenvalues of a dagger a are 0, 1, 2, 3 up to infinity. There's a unique state that's annihilated by the operator A, and to see that we take the inner product of Q prime, an eigenstate of Q with eigenvalue Q prime A, the ground state that we're going to derive, that then substituting for A, this expression here, we get this equation, but Q prime P on anything is h bar over I d to Q prime of whatever's left over. And so we apply this to evaluate this part of the expression and we get a differential equation. This is the differential equation. And it's a first order differential equation, and those are typically soluble. And we solve it, and it's this nice quadratic. And then, because of these very simple commutation relations of A and A dagger, one can show that the Hamiltonian has eigenvalues h bar omega n plus a half, where the state n is A dagger to the nth power on the vacuum state or the ground state divided by square root of n factorial. The identity operator then is a sum of outer products of n particle dyadics, or outer products, and an arbitrary state has an expansion in terms of these eigenstates like this, and it evolves in time like a Fourier series. namely e to the minus iht over h bar on psi, gives us e to the minus I omega t over 2 for the constant term, minus I omega t in like that. And so the wave function evolves this way when we take the inner product with an eigenstate of position, the bra q, and the bra q then, well, that turns out to be the to hn. It's related to hn of x if we set x equal to this combination here, this square root times q. And so qn is then, well, it's this god-awful expression here. If we abbreviate the square root as s, then it's this slightly simpler thing here. It turns out that, and this is particularly relevant to people doing quantum information theory or quantum optics or even physical optics, for every complex number, there's a coherent state alpha, and here's the normalized form of it. It's a normalization factor times e to the alpha a dagger on the vacuum. And so that gives us a sum alpha to the n alpha over square root of n factorial. This is in an eigenstate of the annihilation operator with eigenvalue alpha for every complex number alpha. These states are not orthogonal, but they are what I call super complete, in that if you have any convergent sequence of complex numbers, then the corresponding set of coherent states is complete. That may not be the most natural set of complete coherent states, but it at least is one complete coherent state. We have a few minutes left. Let me do non-relativistic strings. So this is just the kind of string you played with as a kid. You clamp down the ends at x equals 0 and x equal to L. The amplitude then obeys these boundary conditions. If you put this, if you imagine that the height is 0 at x equals 0 and x equal to L, it then, the non-relativistic string then obeys this nice wave equation as long as y is small. And so the functions, these functions satisfy the wave equation and the boundary conditions, and they represent waves traveling along the x-axis with speed v. The space of functions f of x that satisfy the boundary, this boundary condition is spanned by these functions, and we may use this this integral formula to derive for any function its Fourier series in terms of these basis functions, and then we get these coefficients, and then we have another Dirac Comb here in terms of signs. Briefly, in 1 minute, periodic boundary conditions. Well, periodic boundary conditions are what you do when you can't really solve the problem. Or they are what you do if you're studying something that really is periodic, like a crystal. In any case, the idea is to consider a set of, to imagine you have a string and you join both ends. And so, so what you have is that psi of x plus or minus L at time t is the same as psi of x and t. And in 3 dimensions, for a 3-dimensional wave function, you'd have this expression that everything's periodic like that. And if the free Hamiltonian is p squared over 2m, then, and we also impose these boundary conditions, then they require that the momenta are quantized. And so people sometimes say we're putting space in a box when we do this, and then the momenta become discrete. This happens naturally if you're studying a crystal, and in particular, a Bravais lattice has atoms at vertices xi equal to x0 plus a sum ni ai, where the ai are the three primitive vectors of the lattice. And the Hamiltonian of such an infinite crystal is invariant under such translations. If we imagine we have a cubic crystal with lattice spacing A, then the momentum operator generates translations, which generates translations in space. The invariance of H under translations by AN means that the momentum operator commutes with the Hamiltonian. Or actually, we have three momentum operators, one for each of the three dimensions. And so that means that this phase, this exponential and H are compatible normal operators, and their commutator vanishes. They can have simultaneous eigenvalues, and the eigenstates then of e to the I a n dot p is e to the I a k dot n, and where k is the eigenvalue of p, and of course p commutes with h also. And that implies you take an inner product from the left with this ket or the bra x, you get psi of x plus an equals psi, the inner product of x plus an with psi, which is the same thing as x e to the I a p dot n. This is a state that's an eigenstate of p, so we get a k, and then we can pull out the space factor. If we then set psi of x equal to e to the I k dot x times some u, then if you take this expression and this ansatz, you find that u has to be periodic. And for a general Bravais lattice, this Born-von periodic boundary condition then is u of a plus the displacement ni ai is u of x. And these equations are known as Bloch's theorem. I think he was a French mathematical physicist of the middle of the 20th century. All right, well, we're a little over time, but I don't think I should keep you guys waiting. I don't think I should go later, but on the other hand, I'm willing to hang around if I can find some questions. Either shout out some questions anonymously, or I don't see where the hell the chat thing is here. I don't see, I suppose you've been sending me chat messages, but I just do not see them. Does anybody want to shout a question? Oh, wait, here, we've got a chat thing. Okay, does anybody have a question? And have you been able to hear me? Good, you've been able to hear me. Okay, how about a final question or a final question and two? Okay, well, I posted last night the new homework assignment, and I guess we'll start chapter 4 on Thursday, and tomorrow I'll do a group meeting as long as I have electricity. Or if I have to go to my office, I'll do it from my office if I don't have electricity at home. All right, so I'm going to end the meeting now and say goodbye to you all, and hope we all somehow recover. I mean, this is just crazy. No electricity, a storm, and I'm sick. I mean, it's just crazy. All right, I'm going to say goodbye to everybody. So I'm going to stop recording. Oh, wait a minute, there's a question here. When will we get I don't know. If you have questions about your homework, send email to the grader Evgeny will answer your questions. He's quite a nice guy, actually. So send him an email, and he'll tell you about that. I think Wednesdays are the best time to discuss the homework and homework problems. And in fact, one way of dealing with telling the students about solutions is for a student on Wednesday to ask anonymously or in person to ask, one of the two, I don't care which, to ask, how do you do this problem? And at that point, I'll go through it live in video, recorded, and then you'll get the solutions that way. So that may be the solution to all our problems about the homework. I don't know. Anyway, end of meeting. Goodbye, everybody. Stay healthy.